This video is just going to run through the second example of optimization that we didn't get to yesterday. And then after this video, you're going to watch one more video on a couple other examples, and then the rest of the day will be group work. So example 2 is that you have a box with a square base and an open top, and it's to have a volume of 100 cubic centimeters. And it is your goal to find the smallest amount of material required to make such a box. So what you want to look for is, what are you trying to optimize? So here it says find the smallest amount of material. That's what we're trying to optimize. It's going to be a minimum problem. And then our constraint is that we are limited to a box that has 1,000 cubic centimeters. So the first thing is you want to make a sketch. And so it tells you that you have a box within a square base and an open top, but it doesn't tell you anything about the height. And so your square base, the dimensions are going to be x by x, but because it doesn't say that it's a cube, you can't assume that the height is also x. Only the base is a square, and so the height is going to be denoted by the letter y. After that, you want to come up with your equation for optimization. Well, we're trying to minimize the amount of material to use to create this box, and so then that means we are trying to optimize surface area. And then surface area would just be the area of your four sides and your base, and so then you get x squared plus, and then you have four sides that all have dimensions x by y, so the surface area is x squared plus 4xy. What you are limited by is the volume of the box, and the volume of this box is 1,000 cubic centimeters, and the dimensions would be x times y, or x squared y. And now remember, you want to get one of the variables by itself. In this case, I would say that the easiest one is just to get y by itself, then therefore you're not dealing with any square roots, and so y would just be 1,000 divided by x squared. So now I'm going to substitute this 1,000 divided by x squared into my optimization equation, and I get x squared plus 4x times 1,000 divided by x squared. When I simplify that, I get x squared plus 4,000 divided by x. Once you have your optimization equation, then we're looking to find our critical points. So we need our derivative. So dA dx equals, and then just power rule, 2x. You could bring this x up to the top and make it x to the negative 1, and so then your derivative would be negative 4,000 times x to the negative 2, and just bring that x squared back down to the bottom. So there's our derivative to find critical points. We set it equal to 0, and then solve for x from there. So I'm going to add 4,000 x squared to both sides, 4,000 divided by x squared equals 2x. Multiply both sides by x squared to get 4,000 equals 2x cubed. Divide by 2 and then take the cube root, and you end up with a value of 12.599 as your x value. So then from there, we need to determine that this is our minimum, since we are looking to minimize our surface area. So I'm going to do the first derivative test. Something that might look a little different is I'm just going to make a quick number line. I'm not going to make my table. I just know I have to pick a value before 12.599 and pick a value after, plug it into my derivative. So let's say I plug in 10, for instance. I get 2 times 10 is 20. Minus 4,000 divided by 100. So in that case, I get 20 minus 40. I get a negative value. Okay, so I know before 12.599 it is negative. Plug in a number like 15, for example. 2 times 15 is 30, minus 4,000 divided by 15 squared. I think that value would be like 30 minus 17 something. You get a positive value. Therefore, I have a negative and then a positive derivative, and that means my 12.599 is a local minimum. And then from there, make sure you're answering the question. So it said find the smallest amount of material. So I'm not looking for what the dimensions of my bottom of the box are, but what is the amount of material. So I need to plug this into my surface area formula that I had, where it was all in terms of just x. I don't even need to bother with what the height of the box is. And when I plug in 12.599 in for x, I get my surface area to be 476.22 centimeters squared. And so now you're going to watch another video with a couple other examples where you get critical points. You might get multiple critical points, and so then you have to use your first and second derivative test to determine which one's a max, which one's a min, which one am I going to use. These two examples that we did, this example and the one we did yesterday, you were only given one value of x or y, and so it had to have worked to come out to be a minimum or a maximum. But what happens when you have more than one point to test? So that's what the next video will be.